So let's start constructing our Hamiltonian for the hydrogen atom. The electron and the proton each have a mass, me for the electron, mp for the proton, and we expect, therefore, that we will have kinetic energy operators for each of these masses. And we will also have potential energy of some kind. Now, we know that the electron and the proton have opposite charges, so they're attracted to one another electrostatically. And that will mean there's a potential energy associated with moving the electron and the proton apart from one another. And we'll come to that term. So, the Hamiltonian therefore becomes a sum of three terms. This is the kinetic energy operator for the electron. This is the one for the proton. And we have some potential energy that depends on the separation of the electron and the proton. So these here are the position vectors for the electron and the proton, and this modulus here of the difference between these position vectors is just the distance between the electron coordinates and the proton coordinates. And for an electrostatic potential in ordinary free space, that potential only depends on the magnitude of the separation of the two particles. And here, of course, this del squared E refers to the del squared with respect to the electron coordinates, and similarly for del squared P, it will refer to the del squared with respect to the proton coordinates. And this Re, the position vector for the electron, of course we can write it in terms of components if we want to, in the x, y, and z directions, and that's the position vector of the electron coordinates. And similarly for the position vector of the proton coordinates. Now, as I said, the Coulomb potential energy, the potential energy resulting from the electrostatic attraction between the negative electron and the positive proton, only depends on the separation distance between the electron and the proton, and that's this modulus of vector Re minus vector Rp. And the answer to that Coulomb potential energy is that the potential energy is proportional to 1 over the separation, and with a minus sign in here. So the closer these particles get, the more negative the potential energy is. We've chosen the origin of the potential energy to be such that there would be zero potential energy associated with the electron and the proton if they were infinitely far apart. As the electron moves towards the proton, it's sort of running downhill towards the proton, as it were. It's losing energy, so the potential energy is negative. It would take energy to pull the electron away from the proton, and that's why this energy is negative. This here, epsilon naught, is what's nowadays called the electric constant, or it used to be called the dielectric constant of free space. And it's just a dimensioning constant to get our units right here. But the essence is we have an attraction that's proportional to the product of the magnitude of the two charges, both of which are the electronic charge E, on the electron and the proton, one positive and one negative, divided by the separation distance between them, and with some constants here to get the dimensions right, given the system of units we use. This is the version of this equation if we're working in the modern SI units. As we said, this depends on the distance between the electron and the proton coordinates, and that is important in simplifying the solution, that it's only dependent on the distance between them and not on the absolute position of either the electron or the proton. Note it's only the separation between these two vectors that matters, not the absolute position vectors of either of them. So now the Schrödinger equation can be written quite explicitly in this form. It looks a little frightening, but we have the electron kinetic energy here, we have the proton kinetic energy here, we have the Coulomb potential energy here, and then we've written our wave function as a function of all 6 coordinates on the left here and on the right. And because we're looking for energy eigensolutions, we've written this as an eigenequation with the energy we're presumably going to figure out in here.
To deal with this problem, we want to break it up into more manageable parts.
rather than just trying to solve a six-dimensional wave equation. We do this by an intelligent choice of coordinate systems, or equivalently, an intelligent choice of variables, and by separating the resulting differential equation. There are two questions in the choice of coordinate systems or variables. The first question is the coordinates of what? With a single particle, it was obvious to choose that particle's coordinates. With two particles, we might want to choose the separate coordinates of the individual particles. In fact, the problem does not separate conveniently if we do that. We will choose instead what are called center of mass coordinates, and we'll explain what we mean by that. The second question is, what mathematical axes should we choose? For a problem with spherical symmetry like the hydrogen atom, we could make an intelligent guess that the problem would be simpler using spherical polar coordinates rather than the simple Cartesian ones, and that is what we will choose. So let's see how we do this. So let's start to construct our center of mass coordinates that we're going to use to solve this problem. The potential here is only a function of the separation between the electron and the proton, as we've said. And that means that we could usefully choose a new set of 6 coordinates, in which 3 are the relative positions of the electron and the proton. So we could define a new x coordinate mathematically that is the difference between the electron x coordinate and the proton x coordinate. And similarly for y and z coordinates. So we've got a new x, y, and z that express the relative position of the electron and the proton. And hence we have a relative position vector, if we like, r, which is x times I, y times j, and z times k, where these are the usual unit vectors in the x, y, and z directions. And from this, of course, we can obtain that this distance between the electron and the proton is just a square root of the sum of the squares of these coordinates, which is the same thing as this separation we previously wrote down in this form. What should we choose for the other 3 coordinates? We have to deal with 6 of them. We've chosen these 3 as the first 3 we're going to work with, but what are we going to choose for the other 3? Experience with related classical problems, such as a moon orbiting a planet under gravitational attraction, tells us that the position of the center of mass of the moon and the planet is not affected by the orbit of the moon around the planet. Each of them executes an orbit about the center of mass, and we're going to look for a similar approach here. So here's our planet and here's our moon. You might think the moon just goes around the planet and the planet stays fixed. Actually, that's not what happens. The moon and the planet go in slightly opposite directions here, and it's the center of mass between the two of them that remains fixed. This would be obvious if the planet and the moon were of rather similar masses. If they were the same mass, they would actually orbit round about one another like that. And if this one's a bit heavier, then this one doesn't move as much as the other one. But that's the way that we get orbits round about planets by moons. It's actually an orbit round about the center of mass of the two of them. Well, we're going to look at the position, capital vector R here, of the center of mass of 2 masses. So that is the same as the balance point of a lightweight beam. So imagine we had a beam here with 2 masses on opposite ends. And so that balance point is the weighted average of the positions of the 2 individual masses. So somewhere between one end of the beam and the other, we choose the fulcrum, if you like, the balance point, and how far along we choose it depends on how heavy the masses are in the 2 ends. And the answer to that would be that we would choose it at this position. So we've got a weighted average of the electron coordinate position and the proton coordinate position, weighted by the relative amount of mass for the electron compared to the total mass, and the relative amount of mass of the proton compared to the total mass. So that total mass, capital M, is just the sum of the electron and the proton masses. So we're going to try to construct our problem with this as the other set of 3 coordinates, the components of this vector capital R, which we believe represents mathematically the position of what we call the center of mass of these 2 masses. So Now we're going to construct the differential operators we need, and we're going to construct them in terms of these coordinates that we've now chosen. So we've got capital R, which we call capital X times the unit vector in the x direction, plus capital Y times the unit vector in the y direction, plus capital Z times the unit vector in the z direction. And our new coordinates then in the x direction are this x, which is now just the x component of that vector, now explicitly written out. And in the x direction for the relative position coordinate, this little x, which, as before, is the separation of the electron and proton x coordinates. And we'll have similar versions for the y and z directions. So we've got little x's and little y's and little z's referring to the relative position, and capital X's, capital Y's, and capital Z's referring to the center of mass position of the electron and the proton. Well, now we're going to use the standard method that we can use to change partial derivatives to new coordinates. And for this system, this equation looks a little bit daunting, but it's straightforward. And here we're also fully notating the variables that we hold constant, just to make everything as clear as possible. And we're going to do this first for the first derivatives in the x direction. So now the derivative with respect to the electron position with the proton position held constant, we could formally write in the following expression here. And this is a standard expression for changing from one coordinate system to another. So we have d by d capital X with little x held constant multiplied by d capital X by d xe at xp held constant, and similarly for the little x. As I say, if this expression looks a little daunting, please do check it out in the mathematics reference we have, the background materials, to see how it is one comes up with an expression like this. But this is a standard expression used to change coordinate systems for derivatives. Now, d capital X by d xe, you can check that out. You'll find that's just me, the little m, e over capital M. If you look back at the formula that we had for what capital X is in terms of xe and xp. And similarly over here, d little x by d xe, well, that just turns out to be d by dx here with capital X held constant. Again, you can look at the expression we had for little x in terms of xe and xp, and you would evaluate this derivative rather simply as just 1. So, where formerly we had d by dxe at constant xp, that is the same thing as this expression here, which is in terms of partial derivatives with respect to capital X, the center of mass position, and with respect to little x, which is the relative position coordinate. And similarly, we can write for what used to be d by dxp at xe held constant. We work through similar algebra, and we'll get basically the same result here, although now d little x by dxp is minus 1 because little x was xe minus xp. So we've got two expressions that enables us to change from our old way of writing first derivatives to our new way on our new coordinate system. The second derivatives are just a bit more complicated. We have to do the same thing again. And if we work through that, of course, d2 by dxe squared at xp held constant is, of course, by definition, d by dxe at xp held constant of d by dxe at xp held constant. And that, of course, we know what that is. We just worked that out. So we do the derivative again here, and the result of that is all of this expression over here. And we need to work that through, substituting for d by dxe at xp held constant in both of these terms here. We know how to do that. We just work that out. And if we multiply that all together, we get this expression here. Again, a little daunting, but it's straightforward. And now all our partial derivatives on the right-hand side are in terms of little x and big X, with little x or big X held constant appropriately. And similarly, we can work out the second derivative with respect to xp, again at xe held constant. And this is almost the same, but there's a minus sign left over in here that we get from the derivative with respect to xp instead of the derivative with respect to xe. So from this point on, we're not going to explicitly state which variables are held constant. We'll take that as being obvious from now on. Hence, what we have is if we take 1 over me times d2 by dxe squared plus 1 over mp times d2 by dxp squared, adding all these terms together from the previous view graph, we get this expression here. And we can simplify that a little further because me plus mh is just the total mass, capital M, so that cancels out with one of these m's on the bottom line. And we choose to write this object here, 1 over me plus 1 over mp, as 1 over mu. And that mu is something we like to call the reduced mass. And 1 over mu, as we said, is 1 over me plus 1 over mp. Or if you do a little algebra, you can see, therefore, that mu is equal to me mp over me plus mp. Because the proton is very much heavier than the electron, this is almost the electron mass. The bottom line is just a little bigger than the proton mass, and hence it almost cancels with that proton mass on the top line. But we end up with something that is slightly smaller than the electron mass. We can do the same kind of relations here for each of the different Cartesian directions. And so if we define del squared capital R as this here, d2 by d capital X squared plus d2 by d capital Y squared plus d2 by d capital Z squared, and similarly del squared with little r here as this expression with second derivatives with respect to little x, little y, and little z, we can write the Hamiltonian in a new form with these center of mass coordinates. And it becomes this rather simple expression now. So previously we had kinetic energy operators for the electron and for the proton. Now we have new kinds of kinetic energy operators, one with respect to the total mass and the center of mass position, and the other with respect to what we call the reduced mass and the relative position of the electron and the proton. And of course, this vector r in here is just the relative vector between the electron and the proton. And this allows us to separate our problem into two separate three-dimensional problems. So to separate the six-dimensional differential equation using these coordinates, we next presume that we can write our wave function as a product of two three-dimensional wave functions. So this one, capital S of capital R, is something associated with the center of mass motion, and this one, u of little r, is something associated with the relative motion of the electron and the proton. Now, as always when we propose these kinds of separations, this is just an intelligent guess. We don't know that we're going to be able to solve the problem using this proposed form, but we follow through and see if it works. And if it works, because of the uniqueness of solutions to differential equations, then it has to be right. But we justify it at the end, or in Latin, a posteriori, and so we start with this and see if we can get it to work. So we substitute this form into our Schrödinger equation with our Hamiltonian that we've just written down, and we therefore obtain this equation. So it might look a little complicated, but it's essentially straightforward. We've got minus u of r h bar squared over 2m. So that's from the minus h bar squared over 2m and the u of r from here. But the del squared capital R doesn't do anything to the u of little r, so we can bring it out the front. But we are left with del squared of capital S of capital R. And similarly, this part of the Hamiltonian only really operates with little r, so we can bring the S of capital R out here and leave ourselves with this part of the Hamiltonian operating on u of little r. And on the right, we've got our energy times the total wave function. So with this equation here, if we divide by the wave function, the total wave function, and move some terms around, then we can get it into this form. So on the left here, we have all of this, which you'll notice only depends on capital R. And on the right, we have all of these terms, which you'll notice only depend on little r. So, as I said, the left-hand side depends only on capital R, the right-hand side depends only on little r. So both must equal a separation constant. This only depends on one variable, this only depends on the other. And that separation constant we can call E center of mass, or COM, and we put that mathematically on the right-hand side here. Hence, we have two separated equations. We have this equation, minus h bar squared over 2 capital M, the del squared with respect to capital R of S of capital R is equal to some energy, E COM, times S of capital R. And our other equation with EH equal to the total energy minus E center of mass. It's a simple rearrangement we've done to get to that form. So we have two equations, each of which is only in 3 coordinates. And this one is the center of mass motion equation, and this one is the relative motion equation. And we can now solve these separately. This one is really easy to solve. If you look at this equation, it's basically a Schrödinger equation for a particle of mass m in free space. And that has very simple solutions that we know. It's somewhat tricky to normalize them, but we don't need to do that at this point. So these solutions here, e to the I capital K dot capital R, are solutions of this equation. And the eigenenergies associated with those are just h bar squared capital K squared over 2m. So this is exactly like the equation we've had before for an electron in free space, but now we're doing it for a particle of mass capital M. So this is the center of mass motion equation for the entire hydrogen atom. The hydrogen atom has to be able to move about like a particle, so it has an equation that allows it to do that and to describe it. The relative motion equation corresponds to what we will now start to call the internal relative motion of the electron and proton inside the hydrogen atom, to distinguish it from the center of mass motion. And it will give us what we could call the internal states of the hydrogen atom, as opposed to the ones just from the hydrogen atom moving through space. And these internal states are the ones we think of as the orbitals and the energies of a hydrogen atom itself.